All right. We have reached section 3.6, the last section in this chapter of learning integration techniques or differentiation techniques. Sorry, I'm getting ahead of myself here. So this section is officially called Implicit Differentiation and Related Rates. Sometimes we don't really have time to get into related rates. We are going to not cover that this time around. I might have to splice this video later and restate that. But I think for this semester, I really just want to focus on you all learning how to differentiate implicitly in this section without having to worry about the applications of related rates. I probably will be asking you, though, to use the back sides of some of these pages for some additional examples on implicit differentiation. I usually get a lot of questions on these, which is, I don't know, personally, this is one of my favorite topics, but I tend to find that maybe the type of thing that I find to be really fun is not necessarily the kind of thing that you find to be really fun. I mean, it's hard to believe, I know, but either way, we're gonna go through this. I'm gonna give you a bunch of examples so that you feel like you've seen some things and that you're prepared to do your homework and really learn these and excel on your exam. By the way, if you see my lights are just like getting bright and getting dim, I don't know. This house at night, the lights just go up and down and up and down. My husband thinks our house is haunted. It's not. That is silly. If I was going to haunt someone, I wouldn't mess with their lights anyway. Also silly. Implicit differentiation. So the idea here is we're going to find derivatives using implicit differentiation, and we need to determine when it's even necessary to use implicit differentiation. Because, I mean, obviously you're like, why would we even need this? We've gotten this far without it. Yeah, and as time permits, so we're not going to cover the related rates. So implicit differentiation is used to differentiate equations that are not solved as y equals f of x. So pretty much always up to this point, you've seen y equals or f of x equals or g of x equals or h of x equals, and then you've had some function in x that we've just called y or just some other f of x. But right now we're going to be talking about equations that maybe are like x plus y minus 5 equals y squared plus 2x. And some of them, like maybe it's possible that you could solve them for y and then just use your normal differentiation techniques to take the derivative. However, in some cases, it's going to be very, very, very hard for you to solve for y, and you're just going to want to take the derivative implicitly. So I'm going to teach you how to do that. So we're going to first differentiate both sides with respect to x. So that's the first thing we're going to do. So every time you differentiate a y, you must introduce a factor of dy dx. Think chain rule. I'm going to say it repeatedly, but we're going to chain on the derivative dy dx. Okay, now we don't need to worry about chaining this on for x because when we take a derivative of x with respect to x, that's what we've been doing this whole time. I write d dx whenever we're trying to notate a derivative with respect to x. But now we're going to be talking about the derivative of y with respect to x. So that's why we need to include this additional factor. So we are then going to solve for dy dx once we differentiate our terms. Now, if dy dx is in more than one term, and you've seen this notation for the derivative before, by the way, this dy dx. If this is in more than one term, then there are a couple of things we're going to need to do. Maybe all of them, maybe just one or two of them. It kind of depends on the situation. So we are going to get all of your dy dx terms on one side. because remember we're dealing with equations here. And then we're going to get all the non-dy dx terms on the other side. On the other side. Some of you are really going to enjoy this. See, I told you I was going to get excited. I can't help it. Factor out dy dx is the next thing you're going to do. And then we'll solve for dy dx using division. So those were the steps. We're going to perform these steps on all of these examples that I'm going to show you for taking implicit derivatives. So let the fun begin. Example 1. We have x squared plus y squared equals 25. We're going to do a couple different things with this. We have an A, a B, and then there's a C on the other side. So there's a lot going on here. First, we'll go ahead and find the derivative. Now, if you had to solve this equation for y and write it as a function of x, you would get y squared equals 25 minus x squared. And then what would you do? How would you solve for y? You would end up getting, by the way, I'm just sort of going off on like a mini tangent here, but it's absolutely related to the topic. So don't worry about that. 25 minus x squared. In order to solve for y, you'd have to say y equals plus or minus the square root of 25x squared. You actually have two different functions of x there. One of them is a positive radical and the other is negative. So this is not really what you want when you're looking for a derivative with respect to x. It is going to be a lot more straightforward for us to take the derivative using implicit differentiation. So to take this derivative, this one is going to be a little bit more straightforward just because it has a term with only x's in it, a term with only y's in it, and then a term with constants. So we're going to take the derivative of each term. Now, when my term has only x's in it, I don't need to chain on any dy dx's. One thing you do need to watch out for, though, are any instances where maybe you need to use the product rule, maybe you need to use the quotient rule or the chain rule. So we're gonna bring those back into this section, but not just yet. We'll get this method down first. So the derivative of 2x, or I'm sorry, I'm telling you the derivative, but I mean to be telling you what we're doing here. The derivative of x squared with respect to x is 2x. That is not anything different at all. So old news there. The new stuff comes whenever we're taking the derivative of y with respect to x. So you're going to take the derivative of y squared just as, you know, imagine it was just x squared for a minute. Take its derivative. The difference is you're now taking the derivative of y with respect to x. Anytime you take a derivative with a y, every time you differentiate a y, you must introduce a factor of dy dx. So this is where that chain rule comes into play, used a little bit differently here. So we're going to introduce this factor of dy dx equals, and then the derivative of 25 is 0. I tend to find that students, for some reason, forget when they're dealing with an equation to take the derivative of the constant on the right-hand side. It won't always be the case that there's a constant on the right-hand side, but when there is, students tend to just rewrite the constant. So make sure that you're taking the derivative of every single term, including the constants. Okay, so 2x plus 2y, don't forget to chain on that dy dx since we're taking a derivative of a y term, equals 0. Now it says here, solve for dy dx. If it's in more than one term, then get all the dy dx's on one side and all the non-dy dx's on the other side. So we're going to solve for dy dx, just like how you used to solve for a variable in algebra. Same idea here. So I'm going to take my 2y dy dx and leave it on the left-hand side. And then I'm just going to move this 2x to the right-hand side. So when I move it over, change the side, change the sign, I'll just be subtracting it from both sides. Now to solve for dy dx, we're going to use division. So we get all the dy dx's on one side, factor out dy dx. Well, we don't actually really have to do that in this case because we can just solve using division. If we had more than one term with the dy dx in it, we would have to factor that out first. So you will see an example where we need to do that step. But right now we've gotten all the dy dx terms on one side, all the non-dy dx's on the other side, and we'll solve for dy dx using division. So we have negative 2x divided by, and we'll just divide both sides by 2y. And then I can simplify this and just say that dy dx is negative x over y. And that is our derivative of y with respect to x. And I know it looks a little bit different because you're used to seeing derivatives with only x's in them. But we're talking about equations that are not explicitly defined for x. Therefore, you are not going to be expecting that your derivative is only going to have x's in it. So that would be your derivative in this case. Now, part B is asking you to find the equations of the tangent lines at x equals 3. So you might be wondering, like, equations of tangent lines at x equals 3. Well, that doesn't make any sense. Like, why would I have more than one? Oh, it's highly possible, and it's going to happen in this case. Look at your equation here. X squared plus y squared equals 25. Because remember that in order to figure out the equation of a tangent line, we need a point and a slope. And your point needs to be in the form x comma y, like an ordered pair. But right now you don't have that. You only have an x value. So we need to find y. Now it's a little bit different just because we have to solve for y. We usually just have to like evaluate the expression at a given value of x. But it's fine. We can still do this. And we'll say that we have y squared equals 25 minus, and then x we said was equal to 3. So we'll just pop in that 3. And then we have y squared is 25 minus 9, which is 16. And that means that we actually have y equals plus or minus 4. Remember, when you take the square root of both sides of an equation, you need to use that plus or minus sign. Negative 4 squared is 16, positive 4 squared is 16. That's y. So you actually have two different values of y for which the x value is 3. So our points would be 3, 4, and 3, negative 4. Now, if this seems odd, well, think about the actual graph of your equation. X squared plus y squared equals 25 is actually the standard form equation for the graph of a circle. If you don't remember that, maybe it's been a while, but this is a circle centered at the origin with a radius of 5. So it's x squared plus y squared equals r squared. So you have a circle that's centered at the origin with a radius of 5 units. So essentially, I know I'm eyeballing it, and I have to tell you, I have this weakness, and it's graphing circles. I don't know, it seems like it should be the most basic thing, but it is not. I don't know if I've told you about my weakness of graphing circles. Okay, now that was not terrible, I have to say. I was really focused on that. So you have this point here at 0, 5, and then down here you have a point at 5, 0. So what we're looking at is the point at 3, 4. So let's see, 1, 2, 3, 4, 5. So the point 3, 4 is about right. I'm not looking at this straight on, but it's about right here. And then you can see now why you end up having two different y values for x equals 3. It's because you can do the same thing by looking at the circle below the x-axis. And you can get that corresponding point on the bottom half of the circle at 3, -4. So that's why we're focused now on finding equations for 2 different tangent lines. But it's no big deal. We still have the fact that a derivative is a slope, and we found that the derivative, or the general equation for the slope at a given point, was dy dx is -x over y. So once we have that, we can go ahead and just find 2 different equations using a point and a slope. So let's focus first on the point 3, 4. So at the point 3, 4, we have m equals -x over y, so -3/4. And remember that it's kind of nice to actually have this picture because you can sort of check this a little bit. When our slope is negative, it means that the line is going down from left to right. So you can see that definitely at the point 3, 4, the equation line would have to have a negative slope there because it's going down from left to right. Now you're expecting the opposite to happen at this point 3, -4. You're going to see that that tangent line is going to go up from left to right. But in this case at 3, 4, it does have a negative slope. So what we can do is just go ahead and use the point slope form. Y minus y sub 1 is m times x minus x sub 1, and then we'll simplify. Move this down a little bit. Oh, just a little stiffer today. Does not want to be doing math this late at night, but I do. So who cares what the document camera wants? -3/4 x plus 9/4 plus 4, and then you'll simplify. 9/4 plus 4, you can do this in your calculator. Remember, math, enter will give you a fractional value here, but 4 is just 16/4 plus 9 is 25/4. So there's one of your equations, and that's for the tangent line at 3, 4. We'll go ahead and find the other one for your other tangent line. We will do that next. And this will be for the one at 3, -4. And you know, I love orange and it usually doesn't show up, but it seems to be showing up. If you have any complaints, feel free to email me or tell me during the office hour, but it seems like it's showing up okay on the camera. So in this case, we'll have m is still -x over y, -x over y. Well, now you have a negative divided by a negative, so this is positive 3/4 for your slope, which we expected at this point, that the slope would be positive. So we'll go ahead and do, use our point slope form, y minus y sub 1. So y minus -4 is where we get that y plus 4. And then the slope is positive 3/4. And then x minus x sub 1 is x minus 3. So we have done so many of these tangent line problems. You should be so good at them by now. So now we're going to be subtracting 4 from both sides, which gives you -25. Oh, wait. What am I doing? -9/4 minus 16. Hold on. What did I do? I don't know. I don't know. I think I just did it wrong the first time I did it. You know, as I go through your notes, I'm always just like doing a quick glance over at my old notes. Yeah, I just did it wrong the first time. We're good. Everything is fine. Minus 25/4. And then you end up with this situation. And by the way, you can always check that in your calculator by graphing it. Would you like to graph this? Now, remember that in your calculator, you are probably in function mode, and you can only graph circles using 2 different functions, which is why this rewrite is helpful here, because we have to have it solve for y. So let's say we enter the square root of 25 minus x squared. and that gives you the top half of the circle. The negative square root of 25 minus x squared is going to give you the bottom half of the circle. Yeah, that's a negative. Okay. So if you graph this, I'm going to zoom 6 to zoom standard. Oh, goodness. Okay, now it doesn't look very circular. It looks a little bit elliptical, but that's because of our standard zoom. If you zoom 5, it'll zoom square, which means that your axes are, the tick marks are equidistant on the x and y axes. Okay, now if you enter your equations of your tangent lines, one of them was 3/4 x minus 25/4, and the other one was negative 3/4 x plus 25/4. And then you can graph all that. There's that second equation of the tangent line that we found. There's the first one. Sorry, one day I swear I'm going to use an emulator. I just hate all the switching back and forth. Like, let me share the screen, and then I always end up forgetting which one I'm actually sharing. But you can see how we're tangent to both of those points using these two equations. If you're not sure, like, oh, are we exactly at that point? You can always go through and do an intersect and verify that you're actually intersecting the graph at the point 3, 4 and 3, -4. Okay, but those are the two equations. I'm going to make a note to self that this is minus 25. Okay. So that is your equation. Now, the last thing we're going to do here is C. We're going to find the second derivative. I know we haven't used this notation a lot, but remember that it denotes a second derivative. We first learned this notation in section 3.5. We might not have really used it, but the notation just says find a second derivative. What that means is you're going to take your derivative and take its derivative. So now that we have, I'm going to remind you of what the derivative was so that when we go through and find the second derivative, you know what we're doing. So recall from the previous page, dy dx we had as negative x over y. We found that in part A. So now we're going to take the derivative of the derivative. So in order to do that, we have solve for dy dx. We're going to go ahead and take its derivative. So we can go ahead now and say that put our notation back together here. Here's our second derivative. We're going to take our first derivative and find its derivative using the quotient rule. Now, when we use the quotient rule on this expression, it includes variables x and y. So we're going to have to be careful that, yes, we're using the quotient rule, but we're also using our implicit differentiation. So let's do that now. So we'll take, if you're going to want to assign somewhere to put that negative, by the way, I'm just going to leave it in the numerator with the x. We got to pick a place, otherwise we're going to accidentally use it twice or forget to use it. So I'm just going to make the numerator negative and keep the denominator positive. So f prime g. Now, notice, by the way, that when I took the derivative of the numerator, I did not take the derivative of any variable with respect that included a y. This was our variable x, not y. So f prime g, well, we're just rewriting g. We're not taking the derivative of a y variable. So this one can stay as it is. So if it helps you, I can label these if you find it helpful. Pick a non-intrusive color. Again, the numerator can be f and the denominator can be g. And then we can label these. So this will be f prime. G, and then we'll say minus F. Be careful there with the double negative. You want to make sure that that minus sign that's built into the formula gets included, as well as the one that's in your numerator. So there's your F, and then G prime. So G prime is where your implicit differentiation comes in. So the derivative of y with respect to x is just 1 dy dx. Now, you don't have to write the 1, but it is up to you. The derivative of y is 1, and then because you're taking a derivative of a y variable with respect to x, you're going to chain on the dy dx. Or you can just say derivative of y with respect to x is dy dx. Leave it at that. Don't have to get too crazy about it. Okay, so this will be your f prime g, f g prime, and then we'll divide by g squared. Now, again, when you're dividing by g squared, yes, g is y in this case. We're not taking its derivative. We're just rewriting it. That's why we don't chain on a dy dx there. We only chain it on if we're taking a derivative of y with respect to x. So let's go ahead and simplify this. There's a little trick to these, by the way. It's kind of cool, but I'll show you when we get there. First, we'll just simplify what we have. So this is negative y plus x dy dx divided by y squared. One thing I want to say, don't cancel between these two y's. You can't cancel between terms. I know I say that all the time. I'm sorry, but I don't mean to harp on you, but I just see it happen a lot. Don't do that. And you also can't cancel between all three of these y's because this is not like a y, it's a dy dx. So it's not like your standard y that's just sitting there in your expression. It's part of the notation there. Okay, so we have that. Now, officially, this is your second derivative, but it might seem odd to you because you're like, wait, it's my second derivative, but it has a dy dx in it. Aren't we supposed to solve for dy dx? Well, normally when we take a second derivative, what we do is we substitute it out. So I'm going to take this dy dx, and I'm going to substitute it back with its original expression. So we set up here that dy dx was negative x over y. That's how we get around this. We substitute it back in. So we're going to say sub back. We have dy dx is negative x over y. So I'm going to do that in the next step. Sorry, I ended up with an extra little mark there. So where I see the dy dx, I'm going to swap it out for negative x over y. So I still have that I'm using or I'm obtaining my second derivative here. But now I have negative y plus x times negative x over y squared. Now, if you think we're not done yet, you're right. We're not done yet because I can't leave my answer like this. We can't leave our answer with complex fractions. It's just messy. And it's bad simplification. It's not simplified. We're going to have to simplify this. So I taught you a technique that you should have learned in algebra, but if you don't remember it, I'm not surprised because you learned a lot of things in algebra. Some of them you need extensively in calculus, and others you're not going to see again for the rest of your life. But one of the things that I showed you in this class was how to simplify your complex fraction by multiplying every term by the LCD. So I'm going to say here that we're going to simplify, multiply each term by the LCD. And if you don't know what the LCD is, look around at the denominators. We're looking at the denominator of the, I would call it like a subdenominator, but it's the denominator that's inside the fraction that's inside the fraction. So this one's the only one causing us problems. I don't have a complex fraction in the first term. I don't have a complex fraction in the denominator. I only have this y that's causing a problem. So I'm going to multiply by our LCD, which is going to be y in this case. So I'm going to rewrite this I'm going to just write this as a minus, and then x squared over y divided by y squared. This is our second derivative. And I'm going to multiply each term by y to simplify it. I'm very into simplifying the complex fractions. It's important. I don't want it to look like y minus y. So I'll make sure to put parentheses around that negative y. Now, the whole idea is if you've correctly multiplied by the LCD, that extra denominator will cancel out. So now I can say, all right, I've got this y and that y over y is 1, and that will simplify. So now we don't have a complex fraction anymore, and we'll just multiply what's left over. So we have negative y squared minus x squared divided by y cubed. So remember, you got to actually multiply all that in. Negative y squared minus x squared over y cubed. And I have one more trick for you. These implicit second derivatives are not like hard. They're a little tricky. Now, this won't work for all of them, but it will work for this one. First, no, if you're wondering, is she going to have us cancel out some y's? No, I would never have you do some illegal math move like that. But what I am going to do is I'm going to show you something. I'm going to factor out this negative, and then I'm going to switch these terms around, which does not matter, but I think it'll help you to see it more clearly. Okay, so you see what just happened? I didn't change anything. I just factored out the negative, and I changed this to x squared plus y squared. And you might be looking at that and thinking, Faruqi, that looks familiar. It does. It should look familiar because we started out with x squared plus y squared equals 25, if you'll remember, like 20 minutes ago or whenever that was that I started this example. So what I'm going to do now is substitute that back in. And it's going to look great. Recall, x squared plus y squared equals 25. Now, that's not always going to be something that's going to be easy to sub out, but in a lot of cases you will be able to, and it'll make your second derivative a whole lot cleaner, a lot more concise. Okay, so now I can say that we have negative 25 over y cubed, and that is our second derivative. Did I just blow your mind? Sorry. I mean, you're welcome. Anyway, so that's cool. Let's do another example. This one we'll just do a first derivative for. Don't freak out, just first derivative. I feel like this marker, I must have been grading exams and seems to be going. Okay, we'll switch. Example 2. I know you feel like we're already on like example 10, but we're not. That was example 1C we just did. I'm just going to use up the rest of this page on this example. Whether or not we actually need it, it's another story, but just need to fit one example in this space if you're trying to plan that out. Okay, so this is the kind of thing you're going to see often when you are taking derivatives implicitly. Now, one thing I do want you to consider is you're not necessarily forced to take an implicit derivative if you can rewrite the function to not need it. Personally, I like to take implicit derivatives, so I'm happy when they're just written as equations. But you can take this derivative explicitly. In this case, explicit differentiation means that we can solve the equation for y and just use our normal derivative rules. So I'm going to show you how to do it both ways, and then you can compare, and then you'll feel like you have some options in case, let's say you don't remember how to do something like this. Heaven forbid. On a test, I probably would write a question where you wouldn't be able to easily solve for y and you'd be forced to use implicit differentiation. Otherwise, why would I put it on there except just to assess whether or not you can do it? But I do want you to be able to see that it will work both ways. So notice that what I can do with this particular example is I can factor the y out of the left-hand side. And usually if you can factor it out, that sort of like tips you off to, okay, I can solve for y. Now, whether or not you can take the derivative of what's left over is usually another story. But in this case, you can. I can write this as y equals 5 over x plus 2. Technically, you don't need the parentheses, but oh well, I wrote them anyway. So these two equations are saying the exact same thing. One of them is just solve for y and the other one's not. So if I was going to take the derivative of the first form, I would have to use implicit differentiation. But if I was going to take the derivative of the last form, I could do this differentiation explicitly, which I know sounds terrible, but it's not terrible. I know explicit has such a negative connotation. So let's go ahead and take the first derivative, and we'll take the derivative with respect to x, just the same way that we normally would do this, explicitly. So we can say dy dx equals. Now, you have actually one more way of writing this. You can use the quotient rule, or remember that I said when you have a quotient, if the numerator is constant, it's actually easier to just use the product rule with the chain rule. So you have a lot of options here. I'm going to rewrite mine as 5 times the quantity x plus 2 to the negative first power. If I bring it up to the numerator, I'm going to make the exponent negative. And I prefer to use the chain rule. I don't know. Don't you feel like you'd rather use chain rule in this case than quotient rule? It's up to you. You have options. So I'm going to take the derivative by leaving this 5 right where it is. I'm going to bring the exponent down. I'm going to rewrite the inside function, leave it right at just as it is. Decrease the exponent by 1, so you're going more negative. And then multiply by the derivative of the inside function. This uses the chain rule. Uses chain rule. And remember, the 5 just acts as a constant multiple. It's not 5x. If it was, I probably would have said just use the quotient rule. It's just a 5. It's just a constant multiple. So we don't need to worry about any other crazy things occurring here. So dy dx equals negative 5 divided by, and then in the denominator, we have x plus 2 to the positive second power. Okay. Mm-hmm. Yeah. Mm-hmm. All right, so 5 over x plus 2, negative 5 over x plus 2 quantity squared. I'm going to put a box around this, or maybe a cloud, so that we can refer back to it later. Little cloud. I mean, it's officially dy dx. It's done at this point. Stick a fork in it. You don't have to do anything else. But because we're learning implicit differentiation, I want you to see how to do it both ways. So we're going to do implicit next. I don't want to go too high up here. Okay. The next method will be method 2, implicit differentiation. Okay. Now I'm going to go back to this original equation that I gave you, xy plus 2y equals 5. And we're going to differentiate implicitly. Now, You're going to have to remember here that the product rule is going to be required for the first term. You're multiplying two different functions together, and they have different variables in them. That is definitely a case where you're going to need to use the product rule. So I'm going to rewrite this here just so we can really get a good look at what we have right in front of us. Xy plus 2y equals 5. This first term needs the product rule. Use product rule. Okay, and that's just for the first term. The second term doesn't need the product rule. You will have to chain on a dy dx because it's got a y variable on it. On the right-hand side, you're going to get 0. Okay. So let's go ahead and start taking this derivative. Go ahead and get rid of that now. Now, when I use the product rule here, if you want to label your function, be my guest, absolutely label your function. X will be f and y will be g. So when we use the product rule, we're going to take f prime g plus f g prime. So f prime is 1, g is y. Now we haven't taken a derivative yet. We just have rewritten g. So when we write g over again, we haven't taken the derivative. We don't chain on a dy dx. We just rewrote it. That's it. So that's f prime g plus f g prime. G prime is where we take the derivative of y. The derivative of y with respect to x is dy dx. So this is f prime g plus f g prime. Now, this was just the derivative for the first term. Don't be fooled, because I know now it looks like, oh, we have two terms. I started out with two terms. Remember, when you use the product rule, you're introducing an additional term that you didn't have already. So I still need to work on the derivative of the second term. But using the product rule, we get this two-term derivative for xy. Now, I'm just going to go ahead and tell you right now, xy is something that's going to pop up a lot. You're going to see this product a lot when you're working through these problems in this section. So you might even start to memorize that the derivative of xy is y plus x dy dx. That's fine. If you use it a lot, I can't help it if you memorize it. I just want to make sure you understand where it comes from. The derivative of 2y is 2 dy dx. So just take the derivative as though it was 2x, but then chain on the dy dx because it's not 2x, it's 2y. Equals 0. Okay. Now, remember, we have to solve for dy dx. In order to solve for dy dx, I want all the dy dx terms on one side and all the non-dy dx's on the other side. So I have x dy dx plus 2 dy dx equals, and then I'm going to move this y term. I'm going to subtract it off of both sides and move it to the right. Okay, so now I have dy dx times, and this is where I'm going to factor. We didn't have to do this in the previous example, but it says to get all the dy dx terms on one side. We did that. Factor out the dy dx and then solve for it using division. The only way to solve for dy dx at this point is to factor it out and divide. So I have x plus 2 equals negative y. And now I can solve for dy dx by dividing out x plus 2 on both sides. So I have negative y divided by x plus 2. I'm very happy with this dy dx. Now, it's possible that you're noticing that these two dy dx's are not the same. So something must be wrong, right? No. Remember that trick we used in the last example when we substituted a variable back in? Oh, we did a couple different things. We substituted a dy dx. We substituted an x squared plus y squared. In this case, one of these derivatives has a y in it and the other one doesn't. We can go ahead and sub this y out by noting that we solved for y already. Where is it? Here it is. Oh, sorry, you can't see it. Here it is. Okay, so we know that y is 5 over x plus 2. If you solve for y, you can just substitute it back in. I'm going to go, I'm just going to say sub back in for y. Sorry, I don't know where to put this. I would have to zoom out and then you won't be able to see very much. So I'm going to say sub back in for y. Where sub y equals 5 over x plus 2. And then we'll just simplify it out. So now I can say negative 5 over x plus 2 divided by x plus 2. And instead of dividing, you can multiply by the reciprocal. So you're going to be multiplying by 1 over x plus 2. And this leaves you with negative 5 over x plus 2 squared, which is the exact same thing that you got when you took the derivative explicitly. So they're the same. I'm very, very happy with the answer negative y over x plus 2. It's the kind of answer that I would expect in this section, but I do want you to see that they come out the same regardless. That's assuming, because in this case you can solve for y. You won't always be able to do that and take the derivative explicitly. But it will work out in this problem, which is why it was illustrated here. Okay. Let's see what I have next for you. All right, example 3. Oh, I'm going to be able to see example 3, right? Of course you do. Example 3. On the left-hand side, 2x plus y, quantity cubed, equals 3xy. So this is that instance I was just talking about where you're really not going to be able to solve for y here. Imagine if you took 2x plus y and you squared it, and then you multiplied it again by 2x plus y. You would have a whole bunch of terms that have mixed x's and y's in them. You'd have a giant mess on your hands. Be extremely difficult to solve for y. So you're going to have to differentiate implicitly. So we're going to find dy dx. Okay, just dy dx. Now we're going to need a couple of things here. Notice that the left-hand side is going to need the chain rule. Sometimes it's really good to just determine our game plan before we start. We're going to need the chain rule because we have a function that's inside a function other than just x that's being cubed. So the left-hand side needs chain rule, needs the chain rule, and the right-hand side needs the product rule. So we need to recognize both of those things. Now, on the right-hand side, if you want to label your functions f and g, that's fine. I'm just going to put the 3 with the f, and I'll put the g on the y. But let's work from left to right because that tends to be the best way of doing things. All right, so let's go ahead and start taking this derivative. On the left-hand side, bring your exponent down, rewrite the inside function, decrease the exponent by 1. Now here's where you chain on the derivative of the inside function. I'm going to be taking the derivative of 2x plus y with respect to x. Well, the derivative of 2x with respect to x is 2. The derivative of y with respect to x is dy dx, or 1 dy dx, however you want to think about that. This is the derivative of the left-hand side. So just using the chain rule, bring your exponent down, rewrite your inside function, decrease the exponent by 1, chain on the derivative of the inside function. On the right-hand side, I just did the derivative xy, so I'm going to go through this one a little bit faster. F prime g, we're just rewriting g. I don't need to dy dx at this point, plus f g prime. Now I need the dy dx because when I take the derivative of g, I'm taking the derivative of a y. So I know it's sometimes really hard for students to see this. So this is f prime g f g prime. Okay, and then we're going to simplify. Now, this one's a little bit harder to simplify. I find that students tend to have a little bit of a harder time doing this one. My suggestion is to just distribute into this expression. So this 3 times 2x plus y squared, I think about that as just being one quantity. And what you're going to do is you're going to take that one quantity and you're just going to distribute it in. So it's like I'm taking this expression and I'm distributing it into the parentheses. Now I have to do that, otherwise I'm not going to be able to get all the dy dx terms on the left and all the non-dy dx's on the right, or vice versa. It doesn't matter which side you put them on. Somehow I need to get rid of this too. It's a non-dy dx. It cannot stay. So we're going to have to just distribute here so that we can get all the non-dy dx's away. We're going to distribute. This is tricky. For whatever reason, every time I distribute into the parentheses here in implicit differentiation, students get stuck. Please come see me in the office hour if you have questions about this, or go to the tutoring center. You're going to see this happen quite a bit. So don't feel like, oh, I'm probably not going to see this on the homework. You'll see it a lot. I'm going to do another one like this too, just so that you can see a little bit more. So when I distribute into the 2, I'm going to multiply the 3 times 2 to get 6. And then I have 2x plus y squared. And now I'm going to multiply into dy dx. So I'm going to just have 3 times 2x plus y quantity squared dy dx equals, and then the right-hand side's already split up into terms. And that's what I want. I just want terms everywhere so that I can just move terms around. This was not a term, it was a factor we had to split. Okay, but now I just have a collection of terms. I can do whatever I want with moving the dy dx terms whichever direction. If you like having them on the left, unless it just doesn't work very well, I tend to just put them on the left. We tend to, whatever variable we're solving for, we tend to put on the left in math. So I'm going to bring the dy dx's over to the left and the non-dy dx's to the right. So I'm going to keep the 3 times 2x plus y quantity squared dy dx on the left. And then I'm going to bring the 3x dy dx to the other side by subtracting. Change the side, change the sign. The 3y is going to stay on the right-hand side. And then I have one more term I haven't messed with, and it's the first term on the left-hand side. That's a non-dy dx. I'm going to subtract it from both sides so that we have everything split up now. All right, so here's a dy dx on the left, non-dy dx is on the right. Once you do that, you're going to factor the dy dx's out of the left-hand side. Now, it is kind of up to you how you want to bracket everything, or just use multiple parentheses. That's up to you. the right-hand side is just going to stay as is in this step. And then to solve for dy dx, we are going to divide both sides of the equation by this factor of dy dx. I tend to find that once students get to this point, they don't have any trouble. So I'm not too worried about you here. Okay, so there's the right-hand side divided by this factor of dy dx from the left-hand side. Okay, so let's say you got all the way down here and you were like, yep, good, I'm done. You still technically have a common factor that should be canceled. It's not like the end of the world, but every single term has a common factor of 3. I would take that out if I were you personally, but can't make you do anything. I'm going to do this also in the denominator. Are they all 3s? Yes. I was thinking sometimes with symmetry, you'll have the same type of thing happen in the numerator and the denominator. Okay. So when you factor the 3 out, you can cancel it. 3 over 3 is 1, but you have to be able to factor it in order to cancel it. And then you can simplify. So now we can just say we have y minus twice 2x plus y squared divided by 2x plus y squared minus x. Whatever you do, don't cancel out the 2x plus y quantity squared. You cannot do that. You cannot cancel between terms. I'm always telling you all the things you can't do, right? I'm such a party pooper. Okay, so that's the simplified derivative. I'm going to put another example on this page. So I feel like my students tend to always just ask a lot of questions in this section. They just want to see more examples all the time. So I'm going to put one on here. Let's see. I have a whole plethora of examples that I could give you. Let's see. Oh, I had another second derivative question. I had another one where we have to distribute. Maybe we should do that. Yeah, let's do that. Be a good idea. Kind of have 2 that I want to do. We might do another one after this. We'll see. The night is young. I should always record these videos at night. Example 4. Let's do x minus y minus 1 quantity cubed equals x. Now, I want you to find the equation of the tangent line. Equation of the tangent line. And I'm going to give you the point. You need to be able to read said point. 1, negative 1. Okay, so I have another instance here where I need the chain rule. So we're going to do that. And then I'll give you one more after this where you need the product rule. And maybe with a second derivative. Maybe. We'll see. The night is young. I already said that, I know. Okay. Let's take the derivative. I'm going to go ahead and use the chain rule. I'm going to bring this 3 down. I'm going to rewrite the inside function, decrease the exponent by 1, and I'm going to multiply by the derivative of the inside function. The derivative of x with respect to x is 1. The derivative of y with respect to x is dy dx. And the derivative of 1 is 0. So we have this situation on the left, and on the right-hand side, the derivative of x with respect to x is 1. So this is another one of those situations where if I want to get dy dx by itself, I need to distribute. So very similar to the last example. Generally speaking, a lot of times when you use the chain rule, you're going to have to distribute. Do I want to say every single time? No, but most of the time when you use the chain rule with implicit differentiation, you're going to need to distribute. Okay, so I'm going to multiply this whole quantity by 1 and by dy dx. And this is just so we can split this up into terms. Right now we don't have that situation. So we have 3 times x minus y minus 1 quantity squared minus 3 times x minus y minus 1 quantity squared times dy dx equals 1. So we just took that factor of 3 times x minus y minus 1 squared and multiplied it by 1 and multiplied it by dy dx, and we subtracted. So I'm going to leave this. I know I'm like, do I want to leave this? You know why I was hesitating? Normally we leave the dy dx on the left just because it's easier. In this case, it's negative, which is fine. We'll just divide out the negative. That's fine. I tend to not like dividing by negatives because students tend to forget signs sometimes, but we need to practice with it. So, okay, so I'm going to leave the dy dx term on the left. And then I'm going to subtract 3 times x minus y minus 1 squared from both sides. Okay. Now, if you'd like, you can just go through and multiply the whole equation by a -1 and flip all the signs, or you can just go ahead and divide out both sides by this negative value. It is up to you. Now, depending on which side you move your dy dx to, your answer might have all different signs on it. So I'm actually surprised that hasn't come up yet. So I'm going to make a point of that in a minute. But we'll have 1 minus 3 times x minus y minus 1 quantity squared divided by -3 x minus y minus 1 quantity squared. And you end up with this situation, which is fine. We still need to find the slope at 1, -1, but this is technically our dy dx. Now, let's say that at this point up here, you had decided like, well, let's just move the dy dx term to the right and we'll subtract 1 from both sides. You could have done that and all of your signs would have been the exact opposite. Now, I say that mostly just so that you understand that you could be working on the same exact problem with your friend from business calculus, and you might come up with the same or a different derivative than they came up with, but it will still be correct. And mostly that happens when you just have completely different signs on your answer. So like, let's say this was your answer, but your friend who was sitting right next to you the whole time decided like all their signs were going to be opposite. And they ended up with something like this. And then you were like, wait, my friend is so smart and my friend got this and I got that. I must have done something wrong because like, oh, I don't know what I'm doing. I don't know math. And then you panic. Don't do that. First of all, have some confidence in your ability. You might think that you're not very good at math, but you're still in business calc and it takes some know-how to get here. So let's try to have a little confidence, pick it up and say, you know what? I know what I'm doing too. And my friend isn't the only one who knows what they are doing. So we'll figure this out and then you'll go through and you'll be like, wait a second, our answers are actually exactly the same. One of them is just multiplied by -1 over -1. And that will happen. So if every single sign for every single term is different, that's fine. It's still the same answer. Now, I happen to flip the order of subtraction, but that's just like multiplying by -1. So these are the same. Same, Same answer. All different signs. On each term. Okay. So I wanted to make sure to mention that because it doesn't come up yet. Now, I'm trying to find the equation of the tangent line at 1, -1. What that means is I need to first find the slope. The slope is going to occur when I evaluate this at 1, -1. That means everywhere I see x, I need to swap it out with 1, and everywhere I see y, I need to swap it out with -1. These are just in the order in which you see them, x, comma, y. It just means x is 1, y is -1, just like any other ordered pair. So we're going to evaluate this, and I know we're not used to evaluating expressions in more than one variable, but there's a first for everything. So x is 1 minus, and then y is -1 minus 1 squared minus 1. So many ones and -1s. 1 minus -1 minus 1 squared. And we'll simplify. I should have left some more space for that. I did not, but that's okay. All right, so let's see. M is our slope. It's our dy dx at this point. This is going to be 3 times 1 plus 1 minus 1 squared minus 1 divided by 3 times 1 plus 1 minus 1 squared. Got to leave some room for our equation here. 1 plus 1 is 2, minus 1 is 1, squared is 1. So that's 3 minus 1 over just 3. And that means our slope is 2/3. We have a slope of 2/3. We know that our point is at 1, -1. So we'll use point slope form. So we have y minus y sub 1. Well, y sub 1 is -1. So we have y plus 1 equals m times x minus x sub 1. So we have 2/3 x minus 2/3 minus 1. So we have y equals 2/3 x, and then 1 is just 3/3. So -2/3 minus 3/3 is -5/3. And here is the equation of the tangent line to the graph. So I'm trying to figure out how many more examples I want to do. I have 2 that I really want to do. But I must choose one. I've made my decision. It's going to be the second derivative. Okay, now, I've already told you that we're not going to be doing related rates. If you would like to just cover up a related rates problem to put an example down, that's fine. But there's not a whole lot of blank space to write. So I'm just going to put mine on the back of the previous page. So we just were working on page 23. So I'm just going to go to the back of that and put another example down. You know, actually, I'm going to go to the back of page 22 just so my attention is called to it because I'll be looking at both pages. So this was our page 22. I'm just going to flip this over so that it's not forgotten in all the related rate stuff that we left blank. Okay. So let's see. All right, last one. All right. We are going to find the second derivative. Yes, it's like, wait a second, did I do one just like this? No. Example 5, we'll call this. find the second derivative for y squared minus xy equals 8. Ugh. I feel like I'm already having some regrets about this because this might be easier to do. Oh, actually, never mind. No, I was going to say this might be easier to do explicitly, but we actually cannot do this explicitly because it is not easily solved for y. So we're good. Everything's fine. We've got a great case of an implicit derivative here. All right, let's find dy dx. So the derivative of y squared is 2y. Don't forget to chain on your dy dx. Now, your xy is where that product rule comes in. Remember that there's a minus sign in front of it, and you're going to have more than one term behind that minus sign, which means parentheses. Okay, we're going to take f prime g plus f g prime. The derivative of 8 is 0. Okay, did that all happen too fast? Don't put the negative on the x. Just treat the negative in front of the x or as the minus that it is. Just leave it right there. And then here's the derivative of xy, f prime g plus f g prime. Okay, now we'll get all the dy dx's on one side, all the non-dy dx's on the other side. So I have 2y dy dx, and then when I distribute, I'll have minus x dy dx equals, and then I'm just going to move this negative y to the other side. So it's really a negative y, but when I add it to both sides, it becomes positive y. Now, I think that some of you will get very quick with this, and you're not going to feel like you need to factor and divide in 2 steps, but I'm going to just show mine in 2 steps. I'm going to factor out a 2y minus x, and then we'll divide. So now we have dy dx equals y divided by 2y minus x. Okay, so this is an important conclusion because remember that a lot of times we need to reuse the dy dx in our second derivative. So I'm going to put a little cloud around it so we can find it later, but I'm also going to need to use it just so I can take its derivative to find the second derivative. Okay, but that's the first derivative. Now we will find second derivative. Okay. So my second derivative is going to need the quotient rule. When I take the quotient rule, remember that we're going to let the numerator be f and the denominator will be g. So I'm going to take f prime, which is dy dx, times g. Should I label this? I don't know. Do we feel like we still need all these labels? I don't know. Make them faint. F prime g minus f times g prime. G prime is 2 dy dx minus 1. Don't forget, I know sometimes we work on our quotient rule. We forget that there's a denominator on it because we spend so much time focusing on the numerator. I know. I've been guilty of doing the same thing. F prime g minus f g prime. And we'll divide that by g squared. Okay, so this is your g squared. Okay, so f prime is the derivative of y, which is dy dx. G, we're just rewriting, so there's no derivative, so there's no dy dx. minus f. Again, we're just rewriting it. We didn't take its derivative, so no dy dx there. And then when we take g prime, the derivative of 2y is 2 dy dx, because we're taking the derivative with respect to x, and the derivative of x with respect to x is 1. And then we divide it by g squared. Okay, so I'm going to simplify this out a little bit, and then we're going to do a little bit of substituting, because we know that I don't want to have a derivative that has all this derivative notation in it. So let's simplify this out a little bit first. I mean, technically, if you want to be excited about something, we found the second derivative. We just don't have it in a form that's really useful because it recalls the first derivative. Let's see. I'm actually thinking maybe we should just sub it in now and before we even simplify anything. I'll simplify it one time and then we'll drop it in. I'm not going to distribute this, though. That would be crazy, because think about what's happening here. I'm just going to be dropping this in and matching up with this term or this factor. Minus, okay, so we're going to say we have 2y dy dx plus y. So I'm just distributing this y into the parentheses. And then divided by 2y minus x quantity squared. Okay, now, everywhere I see dy dx, I'm going to sub it back out with the expression for dy dx, which is here and here. Ooh, I'm trying to get around all this notation. It's tricky. Okay, so we're going to sub it back. So now I can say that my second derivative, we got a little bit of work to do here, by the way, so I hope you have some space left on your page. I've got my dy dx right now, which is y over 2y minus x times 2y minus x minus 2y times y over 2y minus x plus y. So those are my dy dx's that we're subbing out. It's the only thing that we've changed in this step. Okay. Now, like I said earlier, the really nice thing about this is that when you sub these dy dx's in this first term, you're going to get 2y minus x to cancel here. I'll simplify what we have left because you know we're going to have a complex fraction. We're not upset about it. It just is what it is. It's not going to help to be upset about it. Okay. So we still have a y in the numerator. Just try to keep track of what we actually still have. Then we have minus, and then we have 2y squared over 2y minus x plus y divided by 2y minus x quantity squared. Okay. Now, I kind of want to simplify this a little bit before I do anything else. You might just find that one thing leads you to another. In the numerator here, I have a y plus another y. Go ahead and combine those like terms. Y plus y is 2y. And then we can reassess. Now, we do have a complex fraction here that we're going to simplify. The denominator that's causing you a problem here is this one. So we are going to multiply everywhere, multiply each term by the LCD of your denominators, which is just, in this case, the only one that's causing you a problem, which is 2y minus x. But every single term is going to get multiplied by it. So many pens. Okay. So I'm going to rewrite this, but I'm going to show the multiplication of each term by 2y minus x. And then you'll be able to see how that is going to cancel out and simplify. Every single term gets multiplied by 2y minus x. If it helps you to put parentheses around this denominator, then do that. And then 2y minus x squared in the denominator also gets multiplied by a factor of 2y minus x, every single term. The whole idea here is to get rid of the complex fraction. Simplify what's left. Okay, I'm going to go ahead and distribute here. 4y squared minus 2xy minus 2y squared divided by 2y minus x cubed. 4y squared minus 2y squared is 2y squared. And then you have minus 2xy divided by 2y minus x quantity cubed. You're seeing lots of these repeated factors. So if I were you, I'd look again at that numerator and see if there's anything else that you can simplify. For instance, I know that each term in the numerator has a 2y in it. If I factor that out, I can say, all right, well, I got a 2y here. That leaves me with a y minus a 2x divided by 2y minus x cubed. And then there's actually a little bit more that we can do. I'm going to examine this for a second. Hold on. Oh, you know what? I just realized something. I should have pulled this 2 out. I pulled out a 2y, and there's a y minus, and it should just be a y minus x. I don't know why I did that. Y minus x. Yes, 4y squared minus 2y squared is 2y squared minus 2xy divided by 2y minus x quantity cubed. Okay. Ew. Sorry, I pulled out a 2y, and that leaves me with a y minus x. Get this to erase. And I'm starting to have some level of regret there, because notice that I took out a little bit too much. Yes or no? I mean, okay. I'm looking at the top of my page right now, and I'm noticing it takes forever, right? Y squared minus xy is 8. Y squared minus xy. Remember that. Y squared minus xy is 8. Recall y squared minus xy is 8. And if you're like, why does she keep saying that? Well, go back here, maybe go back here and only take out a 2 instead of a 2y. I know I already did this and I already mangled it once, so I'm just going to rewrite it. Take out a 2 leave yourself a y squared minus xy. And that is coming from here. And then divided by 2y minus x quantity cubed. And then you can recall this fact. And then you'll say, oh, wait a second, you're right. Y squared minus xy is 8. 2 times 8 is my new numerator. Two times 8 is 16, and we'll divide by 2y minus x quantity cubed. And there's your second derivative. All right, I feel like we've seen enough. We've seen enough. Go ahead and get some practice on this. What if I was like, oh, I changed my mind. Let's do related rates after all. You'd be like, no. I know. I can't stay up all night. I have to get to bed. You all get working on your homework and go to the tutoring center if you have questions, because I will not see you again before your test, except for that one little 30-minute office hour before the test. And at that point, we should not have a lot of lingering questions. We should be good to go. So good luck. Email me if you run into any issues, and have so much fun working on your implicit differentiation. It's good stuff.